So this is the second lecture video on the topic of buffer solutions. So I ended up with this image previously, with this slide previously, and I talked about that fact that buffer solutions actually have saturation points, or the points in which they no longer act as a buffer. For this instance, for this particular example, as you can see, the loss of buffer, of the buffering effect of this specific if the specific buffer solution actually is reached sometimes at some point before the 100 mil mark is actually accomplished. And there's something very, very important about this concept. So what happens is you started with a buffer solution in which initially what happens is you actually have, in this case, I hope that this is familiar to you, everyone. So this is acetic acid still. Okay, so you have 0.1 molar of acetic acid, and obviously at that point you have 100 mils of this, and what happens is you have equimolar concentrations of the acid and the actual conjugate base, right? So what happens is if you add, again, you look at this, I want you to compare this molarity. The molarity of this is 0.1 molar. The molarity of what we're adding, the base that we're adding, is actually the same, 0.1 molar. And what happens is if I add 10 mils, the pH actually does not go up very, very dramatically. But what happens is once you reach like around this point, which is around 90 mils, you can see that there's an exponential increase in the pH. Okay, and again, the reason why that is at that point, if I added 100 mils of a 0.1 molar sodium hydroxide, all of this, because this is also 100 mils of a buffer solution, all of the excess, okay, acid and the excess base, specifically more the acid actually gets in this case, have been negated at that point. Okay, so there's actually a way that you can measure the effects of adding a base or an acid to buffer solution, and that's going to be what we're going to be talking about next. So the next thing is we're going to be talking about how do you measure the effects of adding an acid or base to a buffer solution. So this is where the Henderson-Hasselbalch equation comes from, and this equation is just basically written in this form, which is the pH of a buffer solution. This is different than finding the pH of a strong base or a strong acid previously. Now in this case, we're actually looking at the pH of a weak acid or weak base buffer solution. Okay, so two ways that you can measure pH. Okay, so in this case, as you can see, the pH of a buffer solution, which means to say it's a weak acid and a weak base and its conjugate, is dependent upon the Ka, the log of the Ka, the negative log of the Ka, plus the log of however much base, conjugate base, is in solution and how much acid is started in the solution. So this is called the Henderson-Hasselbalch equation, and probably is better if we actually show you an example very quickly here. So here's an example. So we are going to beat this to death, hopefully not to death too much. Acetic acid, you add sodium hydroxide, you have water obviously plus the conjugate base again, sodium acetate. And again, please note that in previous examples, the sodium was not shown and all you saw was like a negative O minus. That's the same, okay? And in some cases, buffer solutions actually do not show you the actual sodium hydroxide again. And the reason why this is because it was the limiting reactant, and you have excess of this plus excess of that at the end, right? So this is the acid again, and then we're adding 0.2 molar sodium hydroxide. What is the pH? So the reason why we can actually do the Henderson-Hasselbalch equation is we have an acid, and obviously the addition of sodium hydroxide drives how much of the conjugate base is actually created. Okay, so if we do the math, if you go to your Ka table, which is in your exam reference sheet, it's actually on page 9, pKa is just the negative log of the Ka. So you take the negative log of the Ka. So the Ka of acetic acid is 1.8 times 10 to the negative 5, plus the log of the base obviously sodium hydroxide, over the acid, which is 2 molar acetic acid. And that is actually how you find the pH. Okay, so the pH of this thing is obviously 3.74. Okay, something very, very important here is when you have something smaller than 1, the log of something, this has a log of smaller than 1, right? 0.2 divided by 2 is definitely smaller than 1. the log of something smaller than 1 is negative, the log of something bigger than 1 is positive. So in this case, you're going to be subtracting from the Ka in this point, okay? I know this might sound confusing to you, but again, all you have to do in order for you to do a weak acid and weak base buffer solution is you go to the table of Kas or Kbs, okay? And you just look for their Kas or Kbs. And then you just take the log of whatever base over the acid. So the acid is always in the denominator, the base is always on the numerator in this case, right? Here you go. So in the previous example, if equal volumes are mixed, you can use the molarities. So this is what's shown here, 0.2 molar sodium hydroxide, 2 molar acetic acid. However, if you have different volumes, but of equal molarity, you can actually use the volume instead of the molarity. Okay, so in this case, this is an example. What is the pH when 10 mils of 0.1 molar sodium hydroxide is mixed with 5 mils of a 0.1 molar hydrofluoric acid? So here we go again. Before, equal volumes of 2 different molarities were mixed. In this case, we have 2 different volumes of the same molarities that are being mixed. And when I say molarity, please again remember that I'm actually talking about normality when we're talking about acids and bases. Okay, so you can use the volume 10 and 5 instead of the molarities, since the molarities in this case will cancel anyway. 0.1 divided by 0.1 is just 1, so you can just, that actually just gets thrown out in the equation. All right, so again, it's the same thing. So where do I find this number? This is the Ka of the acid, the weak acid, hydrofluoric acid. It's in your table, so you take the negative log of that plus the log of 10, which is the base, over 5, which is the acid. That gives you 3.13 plus 0.3. So the resulting pH, when you have a buffer solution and you actually add this much sodium hydroxide to just a pure hydrofluoric acid solution, is 3.43. Okay, now there is a complication, but we're not going to be doing that too much in this class. What happens is, if I give you a weak base, please realize that you can actually transform the Kb into a Ka, and that is actually going to be covered more detail in class if required. But again, if you are going to measure the pH of a buffer solution, it's just chug and plug. You just need to know this equation, and again, this equation is actually given to you in your exam reference sheet as well. And again, the only thing important for this one is you need to find the Ka of the weak acid, and the Ka of the weak acid is normally in page 9 of your exam reference sheet.